Move the horseshoe here. My name is Tim Seymour. I'm the assistant manager for the groundwater section here at the Oregon Water Resources Department. I'm based out of Pendleton, Oregon. And today we're here to present on the Harney Basin groundwater model that was built in collaboration with the model, and then answer some questions. We will, for the first portion of the meeting, primarily be presentation. Steve will go through that, and then afterwards we'll follow up with questions. To be really clear about ground rules here, the USGS does not have anything to do with the regulatory management actions we're talking about taking in this basin. So they're not going to be able to answer questions about how a proposed management scenario might affect the basin. What they will be able to help us answer is how the model can be used, what to expect from it, what the outputs look like, and then Steve, I think, is also going to talk about the model report and the couple of scenarios they ran, trying to understand what a likely future outcome would be under certain conditions. So, Steve, if you want to introduce yourself, and then Amanda and Alex, if you also want to introduce yourselves as members of the USGS, and then we'll get started.
Okay, sure. My name is Steve Kimmer. I'm a research hydrologist working with the USGS, and I'm based out of Florida.
I'm Amanda Garcia, a hydrologist with USGS and lead the groundwater section and helped work on Harney Basin groundwater study.
And I'm Alex Etheridge, I'm Associate Director of the Oregon Water Science Center. Here to support Amanda and Steve.
Perfect, thanks. Well, Steve, I'll turn it over to you.
Okay. All right. Well, thanks everybody for showing up. I'm gonna try to do my best to explain a somewhat complex tool that we built for the Harney Basin. And first, I'll acknowledge my co-authors on the report from the Oregon Water Resources Department, Derek Boschman, who you guys all know. He added a lot of geologic information that helped us build the model. And Jerry Grondin, of course, you guys know him too. He was very instrumental in getting a lot of the pumping information into the model, and with help from Hallie Scheibel, who also did a lot of the programming to get the water use information into our model. So those are the folks that I worked with the most to get this model built and the report written. So I'm going to thank them for that. All right, so my talk kind of divided up into 4 little sections here. Spend a couple of minutes talking about basically what a groundwater model is, and why we use it, and what sort of useful things we can do with it. Then I'll talk a bit about how we used our information from our earlier studies in the Harney Basin to build this particular groundwater model for the basin. And then we'll go ahead, and once we've developed the model, we'll talk about what we can learn from the model about the groundwater system. And finally, as Tim mentioned, I'll go through a few of the future scenarios that we ran that'll help us kind of give us some insight into what might happen in the future under a certain condition. So let's go ahead and start with groundwater model. Why a groundwater model? And groundwater models have been around now about the early 70s or so, and they're kind of been getting more and more developed as time goes on. It's a very common method for hydrologists to study how groundwater systems work. And numerical modeling is used in a lot of different applications, research applications. They do numerical modeling on aerodynamics, like when they figure out how air moves over airplane wings, and they model things like that. Weather forecasting, they can model smoke plumes traveling around. Mining applications, heating applications. There's a lot of things that use this kind of model. And because we can actually turn mathematical equations of the physics of how groundwater flows, we can put that in this model and solve this equation millions and millions of times to get, to give us insight into how groundwater flows. So that's basically what we're doing here is building a tool where we can solve this groundwater flow equation for the whole basin and figure out how groundwater is going to move through different types of rock and with different amounts of recharge and pumping and so on. And it's useful because we can test big systems like the entire basin, something you can't build in a lab, you know, you can't put together an actual physical model of the basin and make it work very easily. So we could use this computer model to do things like that. And so as I said, we can estimate flows and the properties of the rocks with this model. And it's really powerful for looking at future conditions, things that we can't really know unless we have a model like this to test and think about what might happen in the future if recharge changes or pumping changes. We can put all those things in the model, run it forward and get an idea of what might happen. So that's what we're doing here. And we use a model called ModFlow that's been developed starting in the 70s by the USGS, and it's really the worldwide standard that all hydrologists all over the world use to figure out groundwater flow problems. So it's a very well supported and very well used model worldwide. I was thinking this morning, you know, about this point about not being able to build, you know, an actual physical model. But we have a model in our office from the very early days. They built physical models. So we had a big board, like 10 by 10, and they could fill it with resistors, capacitors, which actually mimic the flow of electricity through those things is identical to the equations for the flow of groundwater through the aquifer. So they could actually build electrical models and hook up on oscilloscope, voltmeters, and actually figure out you know, groundwater flow problems with this big, you know, resistor panel. But fortunately, we've got computers now, and I can carry this around and do it anywhere rather than a giant, you know, frame with a electrical model. So the science has come a long way in the past 50 years or so. So before I go into the model, there was a couple of concepts we thought we would just reiterate. These things have been talked about, I think, many, many times, and here in the RAC meetings and the meetings we've put on over time. But some simple ones, an aquifer, when I talk about the aquifer system, an aquifer is really any geologic formation that can transmit water, as they say, to a usable capacity. You know, so it could be water to wells, water to springs, and it's also good to know that an aquifer, like one man's aquifer is another man's, you know, barrier. So it depends. The same aquifer in certain places can be like a poor transmitter of water if you have a lot of very good units around it. But you put that same poor transmitter in another part of the state, and that might be the best they can have. So a unit here that we might call not an aquifer or a barrier or something, if you found that in some other part of the state, that might be the best aquifer they have. So just keep that in mind. An aquifer is really, it's really a gradational type of thing when you talk about what an aquifer and a good aquifer is. As I go through the talk, I'm going to talk about the capacity of the different rocks to transmit water through the system. And a couple of terms that we might use are transmissivity is one, hydraulic conductivity, permeability. In this talk today, I'm going to use those sort of interchangeably. They just talk about how well a certain rock unit will let water pass through it. And as we talked about a lot, recharge basically means water that reaches the groundwater system, either through rain, snow melt, infiltration through streams, irrigation returns, things like that. So I'll be talking a bit about recharge and how that goes in the model. And discharge is another big one. That's any water that leaves the groundwater system. So water that flows out of a spring or flows at base flow into a stream, we call that discharge. Pumping, put a well in and pump out the water, that's discharge from the groundwater system. And another one is evapotranspiration, or what we call ET. So plants that actually have roots that go down into the groundwater system and suck up groundwater and use it. That's also discharging water from the system. And then finally, the term steady state, if I might use that basically in a groundwater system, if your recharge coming in equals your discharge going out, we call that a steady state system, and there's no change in groundwater storage. There'd be no long-term change in groundwater levels because everything is equally balanced. So that's called a kind of a steady state condition. And if you have a condition where you start taking more water out than it's coming in, you're going to see water levels drop, maybe till it reaches a new steady state condition at some other level, something like that. So if I use steady state, that's kind of what I'm referring to. It's kind of the condition before any human influences on the system, maybe before anybody moved here and pumped water out. The system was at a steady state, water going in balanced against the water leaving the system.
I didn't have.
Question? No. Okay, so when we build a model, first thing we want to do is start with what we're calling the hydrostratigraphic framework. So we published a couple reports a few years back that included all that information about the geology and the location of the rocks and the different units in the basin. And we published information about how well they transmit water and so on. So what we end up doing then is build a framework, basically a computer model image of what the aquifer looks like. And all that's described in one of the early reports we put out here, the groundwater resources report, talks all about the geology and so on. So we have this geology, and what we want to do. Go left. Not there. Go left.
We see your arrow.
There, I could see it. Okay. There. Right. So, and then what we do is we divide this geologic framework up into these kind of equal sized boxes. And essentially what we're going to do is solve the groundwater flow equation for every one of these boxes in the model. So again, it's like basically it's figuring out the physics of how groundwater gets into one of the little squares, how it flows out, and things like that. So for any kind of model like this, we basically divide it up into these equal space squares and run the model, run the equations for each of these squares in the model over and over and over again. And that mimics how groundwater flows through the system. So we lay over this grid, we assign, we call the hydrologic properties, how well it transmits water, how it stores water, things like that. And, kind of gets simplified. The geology gets simplified into these different units. And then we also want to represent hydrologic features of the system. So we're going to put recharge. So every box gets a little bit of water in the top from recharge. Maybe where there's a stream located, we get extra water going in that particular cell or box from the stream flow infiltration. And then we represent things like the streams and springs and wells as well. So this, like this green area here represents a well. So those three cells would also have water leaving to account for the pumping that might be happening in that particular box or set of boxes. And we might have these blue squares over here represent a spring where water can leave that particular box and leave the model. So we have to go through for the entire basin and build this to include all the streams and all the springs, all the different geology, all the wells that we have information about. They all get put into this model, and then we run the model for different time steps and with different amounts of recharge and so on, solve these equations over and over again. And it tells us how groundwater is going to move through this model of the aquifer.
Steve, what's the size of the cells?
Those, I'll get to that, but basically for the Harney Basin, they're 2,000 by 2,000 feet. size. So that big. So then you end up with this, a complete model, we're calling a complete model of groundwater system that represents all the hydrology. And then we have to put water in it and figure out, what it does. So, we talked a bit about, okay, so that any generic groundwater model is basically based on those concepts. So then we move here into Hardy Basin. So here's a picture of the basin, kind of showing the elevations that we're dealing with. So we have elevations as high as almost 10,000 feet at the top of Steens Mountain. And our model grid covers an area that goes down to the Malheur River at about 2,600 feet. So we have, nearly or over 7,000 feet of elevation in this model to represent, that's represented in the model. And a lot of that elevation difference is what drives groundwater flow from the high elevation to the low elevation. So the model, of course, has to have those elevations in to get the flow right. So it's kind of the area we're working with. And then this actually kind of shows the extent of the groundwater model, the Mod 6 model. So all the areas in that whatever pinkish tan color are active cells or boxes in the groundwater model. So you can see that we extended it. Keep looking up there. We've got the Harney Basin boundary shown here in this dashed line, but we actually extended our model outside the boundary to make sure we extended it to some other hydrologic features that may or may not influence the groundwater flow in the basin. So we went down to way down into the Alvord Desert where there's springs and things like that get some discharge from on Steens Mountain. So we wanted to make sure we represented, which side of the mountain, maybe some of that recharge up in the top would go to, either east or west. So we gave it a chance to go, east if the groundwater flow equations said it needs to flow that way. And the same thing with going out to the kind of basin along where that Malheur River reaches out here to the far east. And then we kind of followed the watershed topography a lot on the west side of the model. So as I said, about 2,000 feet per side on each model square, and it's 10 layers thick. So one layer, as I say, the top layer is 100 feet thick, and it's got about 75,000 cells representing the basin. So we got 10 of those layers. So we have about 750,000 of those little boxes that we have to solve that groundwater equation for every time that we're interested in. And then actually, some of these cells are outside the boundary of the model because we had to make a square mesh, but we're only interested in the ones inside in the basin or in some of these areas. So we end up with about 480,000 active little boxes in this model that we have to solve the equations for. And they've got a little blow up here just around the Burns area. So you can actually see each of the little squares and kind of how much area they might cover across the basin. So again, we've got about 75,000 cells in a layer, and we've got 10 layers, so about 750,000 cells in the total model.
Steve, did you say they're 100 feet deep each cell?
The top 5 layers, go to the next picture. Not that one. Too far. We'll come back to that. I'll come back to that. I've got a cross section I'll show you. I thought this was kind of a good time to show some of the limitations of the model. So, we talk, we have geologic information around the basin, both on the surface and with depth, based on all the well logs and stuff that we looked at, for the entire basin. So we have a distribution of the geology. These are different units, maybe the basin fill and a volcanic unit and another volcanic unit of different properties here. And as we put that in the model, they kind of get generalized, right? So since we have squares, you know, every one of the squares that might have this unit is red. And squares for this geologic unit are colored pink or whatever, but you can see they're all squares. So in some cases, you know, if the model grid happened to be half red and half pink, we had to look at it and decide, oh, it's probably all pink or probably all red. So things get generalized. You're not gonna have an exact representation of every single geologic unit. You're gonna kind of have a little more smoothed out version as you build this model. And the other thing, I wanted to point out is, for instance, all these dots here are wells that show up in the state's database. And so what happens if you have a 2,000 by 2,000 foot square with maybe 3 or 4 wells in there? They all kind of get generalized and lumped together, right? So a square, say in here, that's got, you see my square?
I think your cursors that you can see on your screen, we can't see on the big screen,
Yes.
and vice versa.
Right, and then you'll have cursor on the big screen. Like that walkthrough right here.
You just use your hand.
Okay, so here's a spot where we've got like 3 wells that need to be in the model, but they're all in the same square. So in the model world, that's just treated as one well. So one of the limitations would be like, I couldn't tell you the water level in here versus the water level in here, and that they might be different. It basically has to generalize them. So that's kind of one of the limitations. We can look at the, you know, the regional things, but I couldn't tell you that, you know, Joe's well 1,000 feet away is gonna have a different head than mine. The model's not gonna tell you that how they interact or anything like that. So it's kind of at the limitation would be at this 2,000 by 2,000 foot square. So we'll get into the wells in a bit though. So we've got this map of we call the hydrostratigraphy. So that was put together and displayed in one of the earlier reports with kind of generalized versions of all the different geology. And why that's important because each of those units might have a slightly different ability to transmit water and store water. So we have to assign them different characteristics in the model. This is kind of the guide to tell us what to assign in the model. We have geologic map. We need to go 10 layers deep so we can know what's going on in 3D. We've got a couple cross sections from east to west and north to south from the model that we can look at. So the top one is the west to east cross section, and it shows the different units, the valley or the basin filling units and the volcanic units in blue, and some other different volcanic units in pink, or the surface lava flows in blue, and so on. So it kind of gives you a flavor of the depth of the model that we're looking at down to about a little higher than 2,000 foot elevation. So we've got, you know, 2 to 7,000 feet of aquifer that we're representing in this model. And you can kind of see the 10 layers represented in there. And really, most of the action that you folks are interested in are kind of in the lowlands around Burns and the flat part. Kind of shows up at the top of the model here in these top 5 layers that reach 100 feet thick. And as we get deeper, we can use thicker layers. And it's also areas where we know less and less about. Very few wells that go down to that depth. So we use a lot of, you know, the geologic interpolation and things like that to handle some of the deeper, more distant parts of the model. And but fortunately, a lot of the, you know, we got to include all those areas, but the groundwater flow, you know, deep up here in the mountains of one of these units is going to have not much impact on the shallow part here where we're doing all of our pumping. So as we get further and further away from our knowledge, we kind of get more general in the model. All right, so we kind of construct this framework of the model, put in the geology. And then with this geologic map, we have information about the transmissivity or the conductivity or the ability of each of these units to transmit water through it. This is based on some of the work, one of the reports that Jerry's spearheaded where they looked at pumping tests throughout the basin, figured out the relative permeability of each of these units. So we're going left to right. These are the units on the left side transmit the most water. And as we go to the right side, they have less ability to transmit water. And generally that corresponds with the younger rocks transmit water better than the older rocks. The older rocks are more weathered, and so on. The fractures may be filled with minerals and things like that. So they generally transmit water not as well. So you can kind of see one of the interesting, most of these on the left side are some of the youngest lava flows that transmit water the best. The ones in the middle, the older basin fill and younger basin fill, and that's kind of what's filling up the lowlands. And in some cases, especially the older basin fill, the range of permeabilities measured cover 6 orders of magnitude. So that's 10,000, 100,000 times. Some of the measurements were 10,000 or 100,000 times lower than some of the other measurements in the lower basin fill. So there's a huge range of permeabilities in the basin fill that we have to deal with in some cases. So this gives us our starting point to fill in the hydrologic properties of all these geologic units in the model. So we plug all that in. It's missing a figure. Now, I haven't used it on this computer. This is supposed to be showing a map, but it's not showing up. So I think we'll have to skip ahead of that. Basically, it's the distribution of all these different permeabilities across the basin. All my figures don't show up with that. Anyway, so we build the model, build the framework, and then we have to run water through the system. So we start with recharge, right? So one of our earlier reports published was all about the water budget and included information about recharge in the Harney Basin. So we use that to determine recharge going into the model. So we show areas, the darker the blue is equivalent to more recharge. So we got higher amounts of recharge in the top of Steens Mountain, some high units way up in the north, up in Snow Mountain. But so we have that distribution kind of for the uplands. And also from the lowlands, we know that stream flow is coming down the streams and coming out into the flats and also recharging the system. So we have that in as well. So these are areas along the Donner Blitzen and the Sylvies and Silver Creek also get water put into those cells to represent stream flow infiltration coming into the lowland. So we have this distribution of recharge all across the basin, but we're also going to simulate through time, right? So we want to do the historic record of how groundwater was flowing in the system. So we decided to go back as far as to start the model with 1930. And we can calculate the relative climate for each year through the model. And that's what this pink chart on the left represents. It's kind of the scaling of this recharge distribution for each year based on high rainfall or low rainfall. So you can see there in the 30s, it's been a dry period, so not a lot of recharge going in. Kind of goes up and down year to year. The big wet period in the mid 80s when everything was flooded and so on. So the big recharge year and so on. So we have entire 80 some years of period of recharge that would go into the model. So so we got to get water into the system, and that's really the only way water gets in is through this recharge distribution. And then we have to count for discharge from the model as well. So we have estimates of groundwater pumpage. I mentioned Jerry and Hallie put together back into the 30s. So for the decades from 1930 through 1980, they did 10-year estimates. So here's the average recharge in the 40s. Here's the average recharge or pumpage in the 50s and 60s and so on. And then what we did was So for each year, say of the forties, it was the same pumpage. And it was the rise and fall is for the annual irrigation cycle each year. So we ran this model on what we call a monthly time step for each of these, for this entire period. So each month had a certain amount of pumpage. The months of October, November through April, May, I forget, April, I think, had just pumpage from private wells and municipal wells and maybe industrial wells from logging, lumber mill at the time, things like that. And then also added was the summer irrigation pumpage, which kind of started in May and ramped up to like July or August was usually the highest month, and then ramped back down in September, and then we turn it off for the year. So that's why we get these spikes of very high irrigation pumpage, and then down the very low numbers that represent the 5% of the pumpage that comes from the other uses, private uses and public well, and so on. So we have this distribution of pumpage through this whole time period as well that can go into the model. And so we have the time series, but we also need to know where, put that pumpage in the model, where it happens. So we also have basically a map coverage of all the wells through that same time period. So this is just an example showing, for instance, the groundwater irrigated field in 1991, not too many. And then as we moved forward through 2018, this shows the addition of groundwater irrigated fields. So all the ones that are circled in black were there in 1990 or so, and then the red ones were added by up through 2018. So that's this particular distribution goes into the model just like this, just as it occurs in real life. And what that looks like when you actually put that in the model, these are 3 layers from the model. The top layer 1, layer 3 is like from 200 to 300 feet. Layer 5 is from 400 to 500 feet, I think. And the all colors, yellows and red colors, are each cell that has a well in it, and it's added up for the amount of pumpage for that particular cell. So some squares might represent 1 well, some squares might represent 5 wells that are all in that system, and it all added up. And then we also had to account for the depth. Some wells are 100 feet deep, a lot of the private wells and so on, ranching wells, stock wells are 100 feet or so. But as we get to the bigger irrigation wells, some of those go down 500, 600. We had a few that actually went down into layer 8, which is, 800 or 1,000 feet below the ground surface. So a few wells even down to layer 8. When you added them all up, private and irrigation wells and public wells and so on, it's about 3,000 wells that we had to account for. And by the end of the simulation in 2018, so we had a very large computer file of pumpage for every month for all these wells for all 80 some years, monthly value for each one. So it's one of the more complex parts of the model of getting all that pumpage figured out and coded in to the model that we could read in it and have it as an input to the model. So once we built the framework, put water in, figure out where water is coming out, we need to do what we call calibration, right? So we want to match what the model is telling us to what we've actually measured through time in the real world, which is the water levels as the aquifer has filled up and drained from water. And we can also match the discharge in the uplands from streams and springs. So we know that a lot of the recharge in the uplands is flowing to a nearby spring or stream and discharging right nearby in the uplands, and then eventually flowing down into the lowland. So we had to represent all those streams in the model. So this plot here has about 9,000 of those 75,000 cells on the top layer were represented as stream cells. And this is a place where water was allowed to leave. If the aquifer filled up to the water level of that stream cell, it would then leave the system through that cell. So we had to represent all that because of, if we didn't have the streams in there, the aquifer in many places would go right up to the top because it's not very permeable. There's enough rain in the upland that would have filled up with water and not correctly accounted for water that's discharging in the stream. So we had to put all these streams in, but basically by hand. You get the elevation of 9,000 different sections of the streams into the model. And then we run the model and we try to match the stream flow measurements that we have gauges around the basin showing different watersheds and how much groundwater is being contributed, flows down through our gauging station. We get a measurement of how much water there is. So we can compare that measurement to the equivalent area of the model where water is coming out of the system. And we get a plot shown over here on the left, right, left. So there's a line up the middle that's kind of a one-to-one line. So if we matched everything perfectly, all those dots would fall right on that one-to-one line, it'd be a perfect fit. Now that's pretty much not possible to get to, but we have a pretty good fit, up through all the different streams. The top two represent the gauges on the lower Sylvies River and the Donner Blitzen River. So we did a pretty good job of matching, the flow coming out of the biggest systems. Some of the smaller ones are a much smaller proportion of water flow. There's a little more variability in there, but overall, the model could match what we've measured in the uplands. It was within 5% of the value, so a pretty good match.
So, excuse me, do you have an R square for that?
I don't have it, no, not in my
I
head.
mean, that would be important for us.
It's probably in the paper.
Is it in the model report?
I can't remember, but put that in there. But we can get it, yeah. So, so basically, yeah, so what that's saying is we're able to match the flow system in the upland. So we wanted to make sure that all the water that's falling in the uplands and moving through the aquifer, we wanted to get the right amount moving into the lowland where like all the action is. And basically this tells us that we're getting the right amount out of the system. So whatever's left that doesn't discharge to these streams could be flowing into the lowlands and acting as recharge to the lowland part of the system. So one of the major, calibration pieces was to get this to match. And the other major thing to match was groundwater levels, right? So as the rocks fill up with water, we can measure that the depth to water and wells all through the basin, see where the groundwater is at. So these dots show just the upland monitoring wells that are part of the monitoring network. And again, the plot on the right there shows the measure against the model results. And we, worked with the permeabilities and storage properties of the upland rocks so we could get it to match this. And that tells us that we're accurately representing the upland flow part of the system. This. All right, so, and then I guess that was probably the easier part. And then when we get to the lowlands, we also have to match the water levels in the lowlands where all the pumping is happening. And we have to do that for an 80-year period, right? So we need to get both, we have a synoptic water level run that was done in about the spring of 2018. So that was kind of what we aimed for at the end of the simulation. We wanted to match that 2018 water level configuration, but we also needed to match all the water levels that got up to that, to get to that point. And that's like 2 years of work to do that basically. So this is an example from the Weaver Spring area. So what we have again is the map here on the right, And we have these green lines represent the contours of the model. So this is the model calculated water level for that area based on all the pumping and recharge that goes into the system and simulated for 80 years. And in 2018, we end up with this distribution, and these are the wells where we have water level measurements. And when you plot up, again, the model against the measured values, you get this plot here on the left. And again, all the dots, you know, in a perfect world, they'd all line up on the line. But in any model that you do, you're never gonna get that perfect. Because of one of the generalization that we had to do, you know, with the 2,000-foot squares, so the geology is generalized, and again, the wells are kind of generalized, and we've got wells with different depths and different pumping rates and different geology down there. So there's a lot of variability. So, you know, we do our best to try to match the overall general trend of the water levels in the area. This is a representation of that. So again, this is kind of the 2018 benchmark we're shooting for. And then we can look at individual monitoring wells in there. So this pink one that pops up represents the well over here on the right, the Harn 52630 and 631, where some monitoring wells with Florida one. It's about 2015. And then the line up there, it says simulated water level. So that's what the model did through the entire time. And you can see starting about what 90s or 2000s, as pumping ramped up, the simulated water level starts to decline and ends up matching really well with what we measured starting in 2015. So that's just an example of probably the toughest place to match was the Weaver Spring area. And I got another nearby example.
Steve, why was the toughest to match? Just curious.
Just because there's so much drawdown. I mean, I had to go from, you know, well, static elevations, what, 4,100, some places down to below 4,000 feet, some more than 100 feet or so a drawdown. And it's kind of not a magic trick, but there's a lot of work to get it to go through that whole simulation and end up where we see it now. And here's another example from kind of the same area where we had two nearby wells with water levels, so the trend goes back further, again, to kind of show that, you know, prior to 1990, it was pretty flat, you know, and our model showed the same thing, you know, maybe all by 5 feet or so, or something like that, not too bad for this big regional model. And then, but we were able to kind of match the beginning of that drawdown and see it decline at the same rate through time. You know, so, but you know, we're in some places we're kind of split the difference. You know, the model predicts a bit lower water level with this particular well, but at the pink well predicts a bit higher water level. You know, so we have to, you got to balance between the two and get something that kind of matches both as best you can. So again, there's a lot of tweaking around, looking at the geology and realizing, well, maybe, you know, this cell we said was sediments, but when you look at the well log, you know, a bunch of wells penetrated a, you know, 30-foot section that looks like cinders. It's really permeable. So maybe that cell should have been a volcanic layer instead of sediment layer. So we go in and change it, you know, and then we get a much better fit. So there's a lot of going back and forth with the well logs and geology and figuring out what's going on to cause, you know, the water levels to act the way they do. So, as I said, that's like years and years of work, pulling your hair out to get that to match. And what I've got here is made a little animation of the drawdown in the lowlands for each decade from the 30s to for 2018. So as I'll start, we'll show, you know, drawdown is basically, it's relative to the 1930 level. So assuming 1930 is kind of, it was actually probably kind of low because it was a dry period, but assume that's kind of a steady state condition, not much pumpage at all. And then we'll run this simulation through time and subtract each decade from the 1930s to see to figure out the differences, the drawdown. That's how much water has been removed from storage. So as I run this, you know, explain what we're going to see. First, for 5 decades, not much at all. There's not much going on. And then we'll start to see a drawdown around the Heinz lumber mill area, because that was one of the early heavy uses, 60s and 70s. And then as we get into the 80s and 90s, we'll see the drawdowns start to grow at Weaver Spring, Crane, and north of Highway 20 mainly. Where it's 230, not much happening. 40s, 50s, I see a little blue dot shows up there around Heinz. 60s, 70s, so that's basically around 1 or 2 wells going on there. 80s, and then the 90s, we start to see the area spread out from 10 and then stopping in 2018. So that's the kind of the area maximum drawdown. So we got, each of these lines represented 10-foot contour. So the deepest one in the center of Weaver Spring, about 100 feet there. So I'll run it one more time. Exciting. Again, yeah. 60s, 70s, a little bit of action. 80s, but then that pumping in the Heinz area pretty much goes away by then, and then we switch to more of the different irrigation wells and how they're showing up. So this is like one of the nice things about the model. We can run these things, and get plots, and help you understand what's happened through time. Okay, so. All right, so we go through that long process, we'll call calibrating the model. So we get to a point and we decide, okay, this represents the groundwater system through time. We're able to match what's going on. We could probably spend another 10 years fiddling around, but we're going to only get incrementally better. We pretty much nailed what's going on with the model. And then we can call it calibrated, and then we can use it to learn things about the system. And some of the things I'll talk about are different components of the water budget that we can't really measure, but the model can give us some insight about, show something about what the historic withdrawal and the effects of that on other discharge mechanisms. And then some of the scenarios that we'll get to at the end here.
Steve, question before you get too far, if it's okay.
Yeah, sure.
When you went through the time lapse and you showed the levels of decline, was that based off a shallow well or deep well or commingling?
That was the top layer of the model, so the top 100 feet.
Just the top 100 feet.
Oh, yeah.
Okay.
So I didn't really have the ability to make a 3D that anyone could understand. So yeah, I mean, I could make that plot for a 500-foot depth, and you could see, maybe different areas would grow different rates, things like that. So I think this is a pretty powerful plot that comes out of the accounting part of the model. We can go through and look at where water's going throughout the entire period of record, both inputs into the model and discharge from the model. So the very top shows volume of recharge through time, and that kind of mimics the earlier plot I showed about. We're putting recharge in, so we're telling it that's what we call it. As far as we know, it's a known thing that this is what's driving the system. So we put the recharge in, and that plot along the top showed, yes, that's what we put in, and that's what it's telling us we put in, so that's good. The gray line represents underflow from the uplands to the lowlands. So what I'm representing here is just the lowland water budget, because that's kind of, again, where we're all mostly interested in. So it shows you flow from the uplands into the lowlands, kind of, a small portion of the budget coming into the lowland system. And then beneath that, under the discharge part of it, shows the different water budget components and discharge from the groundwater system. So we've got the green line represents evapotranspiration, or ET. So there's a part of the model that has numbers for the different rooting depths and usage numbers for stratifieds, right? So the model has a piece that, you know, every time step, it figures out how much plants are taking out of the system, you know, directly from the groundwater. So that's a piece that's shown in green. And the blue line represents the discharge in the lowlands through the springs and stream base flow. So we can see that kind of fluctuating through time. ET is fairly common, or fairly steady through time. It kind of goes up and down a little bit. But as we get into the 90s, and you can see the withdrawal starts to ramp up, that's when the ET starts to drop. Question?
I have a quick question. You said that green line was plants and stuff and what withdrawal from there. I know there's been a huge, influx of juniper trees and stuff like that, that it's straight across. It looks like there's no data that shows anything of any invasive plants or invasive things that might be changing it. Is that in part of the model, or could you not do that?
Remember, this is the lowlands one, so I don't know how much juniper encroachment is in the lowlands. And two, you know, it's based on the water budget that, you know, was generated, you know, for that long time period. So, yeah, that part is in there as well. So this basically just, for the green line declining means probably because water levels are dropping. So certain areas of plants that were using groundwater dropped too deep and they couldn't use it anymore. The streams and springs, again, you can see high, you know, highs and lows for wet periods and dry periods. But again, that value after the 90s started to decline as well. So what kind of shows some other plots of that, but what's useful about this is, you know, there's so many streams and springs that we can't really measure. We don't have measurements from the 30s and 40s to compare, but at least the model can give us an idea of what the relative impacts of all the pumping are on those kind of unseeable parts of the water budget. So I mentioned the withdrawal. You can see that we're getting more and higher as we get up to the 80s. And then what's I think is really fascinating is the very bottom plot is the component of groundwater storage. So that's water that's in the rocks. And we know from steady state that should kind of, if storage isn't changing, you're kind of at a steady state condition. And so based on comparing it to the 1930 condition, you can see as we go through the 30s, a kind of a dry period, we have a kind of a pretty small decline in storage. You know, we have less water coming in, the water levels are going to drop, the water is going to come out of storage. And then we went from the 40s up through the 90s. We were in a period of groundwater surplus, I guess you could call it. So the storage was high. There was more water getting into the system than coming out, and kind of peaking in the mid 80s again with all the really wet periods. But then we kind of turn the corner again in the 90s as pumping ramps up. We move into a condition of always taking more water out than what's getting in. So we have just increasing storage depletion through time, and that's, of course, is represented by the water levels that have been dropped, you know, at this time, same time period, until we get down to about at the end of the model of 2018, when you accumulate all that storage loss from the groundwater system, was about 900,000 acre feet of total storage of cumulative volume taken out of the system through 2018.
Yeah, Steve, I may be jumping ahead here, but, let's say there's a 600,000, acre foot loss. What does that occur? I'm trying to put it in perspective, or maybe the total volume of the basin. Does that make sense?
Yeah, I know what you're saying. I don't have that number. I mean, and I guess it depends. You compare it to the entire basin, including, you know, the way up to the top of the basin and up Stevens Mountain, or I think it's probably more relevant to compare it just to the lowland there, which I haven't done, so I can't give you the answer. But
So Steve, I have a question. So in your calculations, if from, you know, like 14, 15, 16, 17, you know, were really dry years, how much of the percentage of that, you know, the 600, you know, the overusage if you would have just had a normal, you know what I mean, the weather is never the same.
Right.
Does your model take into calculation that dry time?
Yeah, that's the very top line, the brown line, the stream flow infiltration is basically the recharge varying through time, so,
Yeah, well, I guess my question is that if you wouldn't have the dry time, what would have happened to your between your 3 and 600? Does that model have the ability to produce that number?
yeah, you could put in a flat recharge and run a simulation, run the
Right.
same simulation, which I didn't do because I wanted to be.
Right, and I understand that. I'm not being critical. What I'm saying is if you took 23, 24, 20, you know, if that, you carried that out, wouldn't that begin to come back up?
Haven't done it, so I don't know,
Oh.
but it can be done, you know,
Right.
and the models out there. It's certainly,
Yeah, I think that, it's a really neat job, and you did a great work here. The interesting thing, Andy, is that before we were even irrigating, we had a deficit.
Right, that's what I'm saying. Go to that, you know,
So
that's. why-
some of that could easily be associated. We wanna say it's irrigation always, but there's some natural things that are occurring here that show up, and I think it's neat that your model shows that.
right, well, as we move forward, there might be something else that also helps with that. In a couple slides, but, what I've got on this one is, okay, so I looked at the difference between groundwater discharge from all the springs and streams in the 1990s period, like a 5-year period from 88 to 92, kind of before all the pumping started, and then the last 5 years of the simulation. And again, looked at the difference, and this kind of shows where the streams and springs were impacted by the water use during that period. So like the red cells are the most impacted, and yellow less, and gray even less. And if there's zero impact, it doesn't show up like that.
Steve, curious, so we're at one just south of the lake there, I'm assuming it's a side
So
house,
how,
and that's the least amount of development in that area. So are you thinking that development up in the Silver Creek affected the spring down there, or do you think there's any correlation from development in the north or west area to the south?
I think there's development directly south of Side House Spring. And the flow paths are basically from south to north towards that spring, and I think that's where would be, my guess is what's causing it. That's the
So
nearest.
just to be clear, there's no distinction between the effects of the irrigators and the effects of the weather in your model. Like it's the same, they're integrated.
They're both counted in this. model.
Yeah,
This
so
is
you
to
say
match.
it's because of development, we may want to say it's because of the weather, is that right?
Well, I don't know what you might want to say, but.
Yeah. I'm just trying to
Tell you
make sure that
what
point
it
is clear.
is. So, but you can, I've got a simulation.
Well, so Steve, just as a point of clarification there, what we're talking about here is the actual measured. Like the model is calibrated to the actual measured values, right? So what got entered was the actual precipitation.
The actual, yes, and the actual pump.
And the actual pumpage
But I have a
and the
question.
actual water levels.
I still have a question on the pumping levels. You guys did 144,000 acre feet of pumping levels or something. 2 months ago, there was a huge, and that was 3 times almost the amount from the 19, whatever was on your, when you started doing that stuff. And Harney Electric is saying the kilowatt usage only went up 100 times instead of 300 or 285 times. How do you know if the data that you use, the pumping data, is that accurate? And why is there a difference, such a difference between Harney Electric and your guys' values? Because Harney Electric said they only doubled from that account. So I'm just trying to see, you know, okay, this model's great, but if there is some discrepancy in the withdrawal, because I would say there's a pretty good, they need to take that into consideration, their pumping levels. Why is it, you know, wouldn't it be 300 times if you're expanding 300 times? Wouldn't there be some, I'm just saying, the data in and the data, that stuff just seems
Right,
There
okay,
needs to
so,
be some more investigation before the model is really, to me,
so to be clear, it's 3 times.
Yeah.
Right,
yes,
pumpage went from about 50 to about 150.
yes.
3 times, and from what I heard, the Harding Electric said they went up 2 times.
Right, well, 100%, basically,
Well,
double.
that's
It's
2
double.
times, yeah.
But
So,
still, there's 70.7%,
Yeah.
70% difference,
okay,
which is
so,
huge on that thing, and then you take into effect the ground.
okay, right,
Good.
we talked. So one, we went through a very rigorous estimation of the pumpage, based on satellite imagery of all the fields used and so on. And, that's been thoroughly checked and rechecked. So it's kind of the best available thing we've got.
Sure.
If we've got published Harding Electric values, we can look at, and that's been through the same rigorous
Sure.
checking that, everyone expects us to do, then we can look at it and compare it. Okay, so that's one point, I don't have that data. I don't know how good it is. Second point is, if that's true, that the electric data says pumping only doubled during this time,
Mhm.
but we still have the same impacts of drawdown, that means you took a lot less water out, still have a problem.
Which could be drought or,
No, just that's the pumping, what's causing that. So you're saying the effects you're seeing now are caused by 2/3 of the pumping than what we are saying. So that means the aquifer is even worse off by like 1/3 worse than what we're saying here, because the impacts of your less pumping are still the same. Do you understand what I'm saying?
so, yeah, I'm saying it might be from something else, not just the irrigators. Yeah, it is going down, the data's, but the data's what the data is. But is it something else besides the pumping cutting, are we gonna do all these cuts and then it's not really gonna affect it because of the weather, the charge or
The
something?
volumes of recharge kind of pale in comparison to the volumes of pumping.
Okay.
So we're seeing, that's, the model pretty much shows that's the reason. I have some more slides to show. But I just want to, point out, if the argument is that the pumping is really a lot less, but you still have the same bad problems, that just means the aquifer can support even less than what we all think it can, which means you're gonna have to cut things even more. I think that's logically what follows there. So if someone wants to produce those numbers, and come up with a new pumping rate, the state has this model, they can put that in there and see how much lower rates are gonna have to be to fix the drawdown. So certainly can go there.
Well, the rates are gonna be less because you're pumping the water deeper, so, pump. No, calculation. Pump water from 50 feet, it'll pump 1,000, if you take that same pump at 100 feet, it's gonna pump 650.
Sure, but what we care about here are volumes, right, Steve? We're not talking about, nothing in the model talks about rate.
No, because we
It's
can't,
all focused on
we
volume.
can't,
So whether you extract, I get it, 600 gallons a minute or 1,000 gallons a minute, we don't care. What we care is at the end of that day, how much, or that month, how much was actually removed from the system. So volume is what that.
okay, so, kind of to look at that more, I did kind of what we were talking about, I did a simulation where I turned off the pumpage, but ran the simulation just with the clamp, right? So nobody lives here at all. Well, actually, I left in the private wells and the public wells, but no irrigation wells. So no irrigation at all through the whole simulation and run it and see how things change, right? So then I looked at that total amount that pumpage adds up to is about 3,400,000 acre feet through that time period. So let's run the model, but don't take that out of the system. What happens? We get 1.2 million acre feet of increased ET through this time period. We get 1.1 million acre feet of extra stream and spring discharge. And we get 1.1 acre feet of storage, higher storage, no water level drop. And which kind of surprised me that they all came out about equal, 1/3, 1/3, basically. The withdrawal kind of that's happened throughout the history of the pumping in the basin has affected these three things kind of somewhat equally to about these amounts. And that account for,
No, this is over 1930 to 2018.
Oh, God.
So if you just remove pumping from 1930 to
Okay.
2018.
summing up all the water moving through the
Understand.
system through that period. So the model is able to show us this, the relative impacts, even of the things, no one's really measured ET, by plants, through the decades, but we can get a handle on that effect here based on the water levels that drop. And so and that's another piece that's useful to understand, the impacts of pumping through time. And again, this accounts for all the climate changes through that whole period. Okay, our last little piece then would be the future scenarios. So this is where the model can be powerful, but also, you could come up with an infinite number of future things to look at. What if we change this well or that well? And, I've done many projects like this, and sometimes you come up with these, well, what if you pumped here? And the water department's like, well, we're never gonna get access there. That's useless to us, so we try to avoid doing too many scenarios that someone's gonna say, we can't do that, or that's ridiculous. So maybe this was ridiculous, but I did a scenario, just continued 2018 pumpage through the end of the century, 2100. And then looked at what happened. So what I did was I took average recharge for this, because I don't know what the future is gonna be. I don't know how it's gonna go up or down or whatever. So we just took the long-term average that we calculated for the past and ran that into the future. And before you ask, no, I didn't do a climate change scenario. That's another thing that could be done, but we don't have that yet. But so with average recharge going to the future, we run it out and then we can look at results. And here's an example of a well north of Highway 20 on the right here. So, starting about, starts at the end of 2018. So going forward, we have water level declines continuing through the entire rest of the century. And it's about, for that particular case, about 70 foot of decline through time at that particular well. And then the map on the right just shows the contours. Again, these are 10-foot drawdown contours, and kind of as expected, the Weaver Spring area draws down to 200 feet or more, because as you continue pumpage and close to 100 feet maybe in the north and some in distant different parts of Crane. So it just basically shows that water levels are going to keep going down. You're not reaching a steady state where recharge equals discharge at this time frame yet, because we still see decline, not at steady state. And another well, one of the monitoring wells over by the Crane area. Again, we can kind of see this decline. Maybe it's flattening out a little more than the other well, but still, we still see declines and the overall drop of maybe 40 or 50 feet in this particular area. And again, all this depends on how much pumping is in that area, the characteristics of the rocks nearby and all that. It's gonna affect that in some ways. Okay, I think that was it for that one. Okay, and then the second scenario I looked at was, okay, what if we turned off all irrigation in the future and let the system recover? How long would it take to get back to, again, 1990? That will kind of pick that as a starting. So on the left, again, we see a particular well. This is in the Weaver Spring area, recovering. And it's what, about 40, 50 years till it gets back in this particular area to the 1990 level at that particular level. And on the right side, I looked at these different time frames of 10 years, 20 years, 30 years, and figured out which parts of the system recovered to the 1990 levels, you know, within 10 years, within 20 years, and so on. And that's kind of what's colored here. So the dark blue areas recover to their 1990 condition with average future recharge in about less than 10 years. And you can see they match the stream valve. That's where the recharge is going to get in first. Kind of down the Sylvies floodplain, Warm Spring, or, you know, the Silver Creek and Donner Blitzen. And as you move away from those recharge areas and into the areas that heavy pumping, it's taking longer and longer for that recovery. And in some areas of the Weaver Spring is more than 60 years. That would be a future of zero pumping and average recharge going into the future. So that's kind of the distribution. And then for that same scenario, I looked at again the stream and spring recovery for that same condition. And in our water budget report, we kind of looked at 3 areas just to help us with the accounting and everything. And these 3 plots represent the lowland spring and stream discharge for those 3 areas, kind of all summed up. All right, so for instance, the southern region, kind of the red line there, it kind of flattened out. I don't know if we say that quickly or not, the quickest, maybe 40 years for the system to recover back to the kind of normal or untouched stream and spring discharge. The northern region actually recovers the most and takes a bit longer than the southern region. And then the western region out here on the west side really doesn't have as much to recover, but it's still actually recovering at the end of the century. And the reason for that, I think partly is a lot of the springs are way kind of down at the bottom of Warm Springs Valley. And all the pumpage happening way kind of up at the top of the basin. So it's just going to take longer for that pressure signal to make its way kind of through the aquifer and let those springs and streams recover. And also the western region is a really high permeability area, is a large area, this high permeability that's included in the model that kind of will also kind of dictate how long it takes for that recovery to happen. So this is a way we can look at, you know, relative impacts on streams and springs, you know, going into the future. And I could say, as Tim had said, you know, USGS doesn't make recommendations, so we're not out here saying you should not irrigate or anything like that. We're just these are just kind of what ifs we can learn about.
So can you help the group understand, as a modeler, the areas that the timeframes that you've worked in, that you have data for, and that you've calibrated and even looks like done some accuracy assessment, those numbers seem to be most reliable of the numbers that you have. But when you start projecting out into the future, past the plane of any of the data that you've actually had, can you talk about the risks and the need to look at trajectories and not actual outcomes? I mean, you're predicting out into the future and that becomes a much different animal than looking at different things that are happening in the area where your data were collected.
Right. Yeah, I mean, there's certainly unknowns. No, we don't know what the future recharge is going to look like. It could be higher. I doubt it. It probably could be lower. So that's one thing. So this is, yeah, it's a theoretical scenario, but we do know that the physics of what the model represents isn't going to change, right? So we can match the past 80 years of data with an input, and the physics, you know, tells us we're matching that. But when we go into the future, we're really just changing the inputs, and the physics hasn't changed. But the way groundwater flows isn't gonna change, right? So you can quibble about, oh, it's recharge is gonna be higher, it's gonna be lower, or we're gonna, I don't know, invent some different way to pump, or, when things like that will change, but the physics of what's going on isn't gonna change, so that's really solid. So it's a matter of, like, if I were here to say, recharge is gonna be the same for the next 80 years, yeah, someone certainly could argue with that, but
You can't do an accuracy assessment.
not the future. I mean, you
That's what I'm
can,
trying to say.
but I could do, 1,000 runs of different futures, different climates, and you could get a
You
cloud.
can have a probability distribution.
You get a cloud of results and you say, well, it's most likely
Yeah.
gonna fall
Probability
along this,
distribution
right?
is-
No, so that's. The model certainly, available to do that.
Yeah, that's the point I'm trying to make, is you can forecast and have a probability of something happening, but you really can't.
Right, but you also. As working with this stuff for 35 years, you can know. I mean, a lot of it makes, it makes physical sense of what's gonna happen. There you can. Yeah, I'm not gonna predict that, that well is gonna dry up in, 2023 or 2033 or something like that. I'm not gonna go, make any prediction about a particular well or particular water level at a certain spot, other than this information shows us likely, here's the way it's gonna go. These all might be off by a couple hundred feet, acre feet, either one way or the other, but, it's pretty solid of what the trend is gonna be.
Is the western region more problematic on your last couple of slides because of Weaver Springs and the geology that surrounds Weaver Springs? Well, clumping into the western region?
And problematic in what, in this one?
Recovery, yeah.
I wouldn't necessarily say so, because there's not really too many spring or stream discharges that near to the Weaver Spring area, so I don't think it's affecting them. It's more, the upgradient stuff. I mean, the most problematic part of that is there's a real lack of a whole lot of wells, up on that going further out, so we identified this as a strange high permeability feature in a bunch of different wells. We're able to match that with the model, but we don't necessarily know what's causing it. So there's certain springs and things out there that we're probably a little less, confident about what's gonna happen there. But it's also an area where there's not much going on. So I think people were more interested in what's going on closer to town here.
And it's also, as Steve mentioned earlier, the distance between the recharge area and the discharge area. So it's just gonna take longer for the water to move and for that pressure gradient to make it down to that area versus like somewhere like along Highway 20, that's pretty close to the recharge area there. You have that upland recharge that's moving down. You also have losses from streams that are coming out of the mountains into the valley. So that's replenishing a lot of groundwater there. So that's why it jumps back faster.
So on that point, 2 slides back, the most interesting part of looking through this was Silver Creek. Because when we set multiple meetings here, we talked about dry mountain, we talked about it with some of the younger geology and potentially in some recharge. But when you shut off the water, it's one of the largest time lapses to respond. So that was difficult for us sitting through the study with you guys. What's the plausible explanation for that?
So what you said about Silver Creek is that it's a large area, and it's high permeability, right? So when you draw down a large high permeability area, you don't see steep cones of depression, you see gradual, small reductions in water flow, right? But you see a big cone of depression. And so when you go to fill in a big cone of depression, you need a lot more water, right? So
It could be, does that then, I guess you'd have to calculate the volume of each one really and say it, but Weaver Spring is relatively,
Matt, it's
Weeds in
relatively
there.
small compared to.
it's smaller, but way deeper, whereas that, western region, it's 10, 20, 30 times bigger, but you know, maybe 10 or 20 feet of drawdown. You multiply all that out, which I haven't done, you could probably figure out the volumes of each and maybe help me understand it. This, again, the model, you can get that stuff out of the model.
So it is strictly a volumetric reading in time. So I mean, Weaver Springs is 1,000,000 gallons and Silver Creek is 1,000,000 gallons because it's spread farther out. Is that what you're trying to infer? I'm just
Yeah.
curious.
Yeah.
Okay.
So the geology makes it manifest differently in the different areas.
Could we go back 2 slides? There you go.
Let me, we can do that. I think I have
Oh, you
2
can,
more slides. Let me finish up.
Yeah.
This was just that same final scenario. Again, I plotted the streams and springs that would show the most recovery. Again, kind of just to show an aerial picture. Again, you get the sod house area, some out here in the Warm Springs Valley area, and it kind of surprised me. A lot of that northern region, you get a recovery at the kind of the mouth of Sage Hen Valley, which I don't know, isn't really talked about that much. But, you know, a lot of the old maps show a lot of swampy land and springs in there. I don't know too much about the area now, but it seems like perhaps that area was impacted by pumping in the Sage Hen Valley. If that goes away, you'd have a bunch of recovery focused in that area there. Water levels would come up above the ground surface. And then, so that's the last map, and then just wanted to reiterate the take-home messages. And basically, the model has been built and it's able to match 80 years of the historic water level record and the base flow record from the uplands. And we're able to match those lowland water level declines in different areas, even the most heavily pumped and strange geologic areas. We're able to get a pretty good match of that trend. And we talked about the historic withdrawal, and I took that away and looked at what impacts there were on the other forms of discharge. They all came out kind of relatively equal between the ET, streams and springs, and the groundwater storage decline. And kind of the easiest one to understand, if you keep pumping at the 2018 rates through the rest of the century with average recharge, then declines are gonna get deeper and they're gonna spread. And then the last scenario, you stop pumping, the recovery is gonna vary spatially depending on where the drawdown was biggest and where you might be closer to recharge. Though some areas maybe under the stream, directly under the river, floodplains and stuff could be 10 years, whereas other areas is more than 60 years to recover to a 1990 level. And again, who picked 1990 just because that seemed to be about when things started to go to the decline side of things. And we've got one more thing that we're working on, a partner with someone from Oregon State. That talked to some of you guys, Bill Yeager and others in the economic department, and they've developed a sort of somewhat complex economic model of irrigation, water use and pumping, and we've coupled that with our model. So we ran 30-year scenarios into the future that iterated between the model and the economic model. So you make an economic decision, okay, we're gonna pump all these fields, we run the model for 1 year at this pumping rate, and there's a certain amount of decline, some of those wells have to go off, and there's economic decisions that go with it, and so on. So we got that, it's actually been reviewed, and it's at a journal, scientific journal, water resource journal right now, waiting for final approval. So we're hoping any week or month now, that'll be published and that'll be available as well. And for folks at OWRD to also use to help them look at some of the different scenarios we ran there. So that's hopefully coming soon. And yeah, that's it. Question. We have a new report. I saw some copy back there. That's got all this in painful detail for anybody that wants to read it all. Answer more questions.
I think we have a question.
Okay.
So we have a couple of questions online. Do you mind unsharing the screen, Tim? That way we can see everybody. Yeah. Okay, so first question from Amy, was the pump test data from well logs or actual pump tests?
Both. That's documented in the OWRD report where they had pumping tests and well drawdown tests and a variety of things like that. It was like 1,400 different tests throughout the basin.
Okay, and then Ken Beerley had some questions too. Ken, do you want to go online and talk about those, or Amy, did we answer your question?
Yes, I was just curious about those inputs of the pump test information to determine the hydrogeology, the permeability and the flow rates.
Yeah, I had a couple of questions. It's pretty clear that there are very few wells in the western region, particularly on the far west side of it. But also it seemed like there's a number of faults that kind of parallel Silver Creek. Do you have any idea whether that has a potential to affect groundwater flow in that area?
The faults?
Yes.
I suspect that's a large part of what's driving the flow directions down towards the Warm Springs Valley. It might be what's causing some of the higher permeability area that we've seen, but not figured out exactly what's causing it. But one of our likely suspects is that's kind of part of that Brothers Fault Zone that runs in that direction. And that might be contributing to a lot of the permeability in that area.
Thank you. And the other question is just what is the economic journal that Bill Jager's publishing in? Do you know the name of it? So we can look for advanced articles.
Water Resources Research.
Okay,
So
thank you.
Hydrology journal. Okay. Yeah.
And then we have two more. Sorry, gentlemen, I don't know what order it was, so I'm just going to go with who I see first. So Gus, you want to go ahead?
Yes, thank you. First of all, Steve, thank you so much for the presentation. I know how much work this is developing models, and especially at this scale, very tricky. Couple of quick, one quick comment. The data release appears to be missing the EVT input file, so I'm not sure. The model still runs. I'm familiar more with ModFlow. This is kind of my first foray into ModFlow 6, so just letting you know if that's something that needs to be added in to the data release. Second question, and I have a few. Oh, sorry.
What file? The EVT file?
Yes, the EVT package input.
It's not in there. Is that what you're saying?
Correct. It's
Okay.
listed in the it's listed in the name file, but it's not actually in the model files that were available.
Right. I can double check that. It should be. If not, I'll stick it in there. Yeah, that's the parameters for the evapotranspiration package in the model. We had others download it and didn't tell me that. So yeah, I'll double check.
Yeah, like I said, it runs without it, and so like I said, this is my first time really getting into the nuts and bolts of ModFlow 6. So I'm trying to figure out how it differs from ModFlow, but just sort of letting you know, because I know that it's very easy for files to get misplaced when you have so many of them.
Right. Okay.
My first question is, and I have several, so feel free to bounce back and forth to other people. First one is that you represent the streams as drains. And so one is, how accurate do you think this assumption is? Because then that means that as soon as that water leaves the model, then it's gone and it can't be, infiltrated further downstream. And I understand why you did that from a modeling perspective. I'm just curious from a water budget perspective, if you think that is fairly accurate.
I do, because we then add that water back in kind of manually in the recharge package. And we felt that was a better way to represent it, partly because we have zero information on stream characteristics for the, hundreds of thousands of miles of stream as far as infiltration rates and, all the stuff that goes in the stream flow routing package. So we thought for a big regional model like this, we could just represent them as drains, and then any water as we know, it gets down to the lowlands and acts as recharge. So we have estimates of that. So we put it back in to keep the water budget, accurate.
And then a follow-up question to that, has there been any comparison to, for example, like, monthly flow volumes in a specific stream reach? And if you have any flow observations and trying to compare if the model is actually producing the same, roughly the same volume of stream flow for a specific reach?
Well, the only what's accumulated at the gauging stations, right? So whatever's upstream of the gauging station, we summed all that up. I mean, we know with the extreme amount of relief that the model has to represent, and again, the 2,000 foot square cell, we put an elevation for that. But, if you're in a canyon or something, you've got a couple hundred feet of relief in that you're averaging. So it's not, it's for a regional model like this, it's just not really appropriate to try to, pick a mile reach and try to see if you're matching that exactly. So we went with the using the gauging stations because they integrate, a larger part. And really what we're interested in is the volume of water staying subsurface into the lowlands. We know if we get the right amount of water out of the system at base flow, we should do a pretty good job of what's left is going into the lowlands. So that's why we did it that way.
Sorry, can you explain how did you implement gauges if you're not using the streamflow routing package?
We know the gauge locations, and we summed up all the drain discharges upstream on a stream network from it. Right. And then that's the one plot I showed the comparison between measured and model.
Okay, thank you.
Thanks.
Are there any other?
Yeah, we have one more. Sorry, one more online, then we can go to the room. Greg, go ahead.
Yeah, hi, I'm Greg Capillas with Pacific Hydrogeology, and I'm here with my wife and business partner, Malia Capillas. Anyway, we attended the commission meeting back in October in Burns, and went on the tour, and during that tour, we learned that that Malheur Lake, the levels in Malheur Lake increased, I guess, significantly, and I forget exactly the time period, but it was, within, I think the last decade or so, at some period, levels in the lake came way up, and they didn't go back down, I guess, until recently, the recent kind of drought that we've gotten into, the drought period. And I know this isn't really maybe a little model related question, but it is related to the whole system and how it works. And I'm just kind of wondering if you have an explanation for what happened there.
Are you talking about the flood period in the 80s, right? Where the
16, 17.
or 2016, 2017?
Lake level came up quite a bit in 2016, 2017.
Right.
I'm assuming I could be wrong.
Are you talking about the most recent, or are you talking about the?
Yes, the most recent. Yeah,
I mean, the easy answer is it rained more. And I guess I'm not quite sure what else you're getting at. I mean, from the modeling perspective, from all the indications we have, the lake, especially the Malheur Lake, seems relatively uncoupled with the groundwater system. There's some discharge down there, and if the lake level was up like in the 1980s period, it was, there was probably some spread out enough that there was maybe some recharge, but it's pretty much at the discharge end of the system anyway. So from what we believe we understand, that, I mean, the lake level was almost entirely controlled by the winter runoff, and not much really coupled with the groundwater system.
okay. And then the only other question I had was you mentioned that some deeper wells in 800 to 1,000 foot depth range. And where are those located? Are those located mostly in the Weaver Spring area?
They're spread out throughout. I haven't looked at that probably in over a year, so I couldn't tell you exactly, but it was like 3 or 4, you know, that maybe went down 800, 850, maybe 1,000 foot, one well. I can't remember the exact details, but I don't think it was focused in any one area.
Okay, thank you.
Danny? Yeah, so after watching the presentation, would it be fair to say that the lowlands are hydraulically connected?
To what?
You know, the hydrology of the water would move through the entire valley.
Yeah, I mean, based on, you know, the modeling that we see in the water levels we see there, we don't see any kind of, you know, barriers or anything like that. Most of the, you know, eventually, you know, if you suppose if I ran the scenario of pumping, you know, for 3 more centuries, you know, that drawdown cone from Weaver Spring might spread across the entire basin.
But the water would run north to south.
Well, once you put a giant depression in there, you're gonna change the flow directions towards that, you know, that Weaver Spring area is now the low point in that area of the basin, and groundwater that maybe used to flow, say, to Harney Lake, in some areas might come and now being drawn towards that area with even lower pressure than the outlets at Harney Lake, for instance. So it's really, I mean, it's a matter of time and geology that, you know, that connection in some areas is going to be faster than others and so on, but there's no indication that there's absolutely there's an absolute barrier between one area or the other. It's really just a matter of time, and that's kind of the value of the model. You could run it long enough and try to figure out what that time would be, you know, for a particular area. And from what I understand, you know, OWRD is already, you know, learning how to run it and look at these, you know, different sub areas that they're looking at, and they can, you know, pump different areas and see how that impacts nearby sub areas and all that. So the model will be able to look at things like that.
Yeah, that's what I was trying to understand is how you manage a sub area if it's all hydraulically connected. You know, you turn this water off and your neighbor's using, you know what I'm saying? I can't wrap my head around it.
Well,
I mean, if you put a straw in the bowl,
yeah, I mean, it's a little more complicated because of the geology again and the time. And, you know, yeah, that's why we have to build a model, basically, because some of those you can't, there's too many variables to, you know, to do on paper. So the model lets you do that. But as far as how they're gonna manage, I get to point at them.
right, I understand it, but I was trying to understand what, you know, if you create a sub area, what have you really accomplished?
I mean,
Sure, and I think that's a conversation for the RAC.
Let me rephrase that question a little bit, if you don't mind.
Well, I just, yeah.
Steve, can the model be used to look at how sub-area management could be effective? Can the model be used to try to figure out possibly what a permissible total withdrawal in a sub-area would and what effects it would have?
oh, yeah,
And would it be a good model to do that with?
absolutely.
And is that why we developed the model, or to use it for these management scenarios?
I think that's part of it, you know, that's certainly what us modelers tout, like, this is a great tool to management.
Could it be even more accurate as a hydrograph approach to try to figure out PTW?
Possibly, it could help you with more complex ways, but it could also, you could also use it to verify that hydrograph way, like if they both match, like, so you look at, you know, this work.
Going to different subject, on this, in the groundwater study, does it explicitly state that it's all one groundwater reservoir?
In the study, it says that it's one interconnected system.
So with pumping in the north, within a couple hundred years, will it ever affect pumping in the south?
I'd have to run the model and see.
In your educated opinion, you think it would?
It depends where, it depends where you're saying north and south are, I guess. I mean, if I pumped at the top.
He wants Grant County and the steam. That's what he's asking.
I would bet that if you pumped in Grant County, you wouldn't draw down water in the steam.
Okay.
And how long does it take to do a model or to run one? Is it a week? Is it 6 months?
It's about 2.5 hours
2.5 hours.
on
So
my laptop there.
you could do several runs for us in a matter of a week or two.
So-
That could be done.
Yeah, so that's something else we're gonna talk about as we move forward, is what that time looks like. So pressing, like, developing input files takes time, right? Because you have to tell the model what to do. And then pressing go and having it do its calculations, right? So that's what takes a couple hours.
But the hard part is figuring out
Then,
what I'm putting in.
right, so you have to figure out what to put in, and then you hit go, and then what comes out isn't these nice graphs and charts and maps and whatnot, right? You then have to take the data that comes out, process it, and put it into that. So I, totally, I understand where you're going with the question. What we're trying to build is the tools to be able to do it quickly. Because we would like to run model scenarios for a lot of these, potential options. But we need to be able to, we need to be able to look at the outputs equally from each, so that we can actually evaluate the success of whatever the scenario was we put in. And maybe success is the wrong term, but like the outcome of whatever the scenario was we put in. And that's the more challenging part. And that's what we are actively working on and spending a substantial amount of time to get to.
Won't that be addressed in the agenda this afternoon when we talk about modeling or start to talk about modeling?
Yeah, as we start framing the conversation, we'll start to have conversations around that as well.
I mean, it hopefully looks good on the screen, but you're basically dealing with a lot of files and numbers, right? And you run this model and you get a mile-long text file with water levels and things like that you have to understand.
Yeah.
Some of the outputs, I don't know if you know computer stuff, but like makes like an 80 gigabyte output file for the water budget. That fills up half your computer, and you need the proper software to get in there and extract, stream flow from a certain stream, things like that. So there's a lot of pre and post processing that has to go along with it to get usable information out of it. So, yeah, it takes a while to generate an input file, run the model, extract the output files and turn it into something, that you can understand.
So John, you had a question that I think we've got one online we're gonna jump to, so.
Okay. One question, I guess, is, it looked like this was basically 3 parts of the basin. And if, Tim, we're looking at 15 parts, how do we apply one to the other?
Sure, so again, that's something we'll talk about later.
Okay,
But for Steve, from Steve's perspective, right, with the report, you were looking at 3 regions because that's what we divided the basin into for this.
For the water budget,
For the
yes,
water
just so I could compare apples to apples, the model to the water budget report. I wanted to show that here's what we thought, the water budget was doing. Here's how the model matches that, right? So I had the model is just, one unit, but I just extract out data from the southern side, so it's not working independently from the south to the west to the east, north. It's all the same. It's just,
okay,
I can win and, draw a circle around the results and add up all the results inside there. And that's the southern, results. So.
And so we can do the same thing spatially going forward with whatever boundaries we choose.
okay.
So
And that would also show, as far as ODW and a voluntary agreement, it looks like that would show some idea of how long it's gonna take for the aquifer to respond. I mean, if an area is going to be cut back by 50%, it looks like your model could tell us okay, that will be back to a stable level, within 50 years.
Right, right. So one of the key inputs we're gonna tweak is pumping and where pumping is located. And then outputs from the model, Steve, we can get, what are the key outputs that we can get from the model, right?
Water levels everywhere,
Right,
stream and spring discharge
right,
for all those 9,000 points if you wanted them. A water budget file that you can sort out in different ways, you know, you can get the total basin flows, or you can, like I say, you know, draw a polygon around some area, 15 areas or 30 areas or whatever. It's like, give me, you know, add up all the numbers inside there, what's going in, what's going out.
right.
So you can get a budget for any area, you can get the water levels for all 10 layers for anywhere in the model.
And then does it include ET as well?
Yes.
Like, would we be, so we'd be able to
That's the
estimate,
water
like,
budget.
right, okay, so that's part of the water. budget.
Yeah.
But yeah, so like to your question, John, about, and I'm just trying to infer, like, when you say ODF and W, I assume.
Oh, I'm sorry, I meant OWRD.
Oh, okay, all right, well then we'll stop thinking about that.
Yeah.
But yeah, I think the natural discharge mechanisms, evapotranspiration, spring and stream discharge are also gonna like be interesting to look at and see what happens. Because as Steve showed, it's basically 1/3, 1/3, 1/3 is what pumping seems to take from. So if you pump 90 acre feet, it seems that 30 acre feet of that would have gone to plant, like natural discharge through evapotranspiration and, you know, groundwater dependent ecosystem plants. 30 acre feet would have gone to some sort of spring discharge or stream discharge, and 30% comes from groundwater storage, and that results in lowering the water. So,
But that was since 1930, I mean, it's not like, those plants that could have been lost in the first 10 years. As all. as far
Well,
as
there was
root
no
depths or
pumping,
whatever.
there was no pumping of interest till 1990, you know, so none of those impacts really kicked in until we.
yeah, but what I'm trying to say is, that it will be interesting to see from an output standpoint, what then happens around that area that we have made a management decision and created a management scenario for and changed the pumping.
I just want to make one comment, that really worries me to hear you talk about trying to make these longer term predictions for these guys and models, even though they have some physiological basis. I've been modeling for 40 years and do modeling of invasive plant dynamics. And I'll tell you a little story that struck me and sticks in my memory, which is, I went to Washington DC to one of the climate hubs to talk with them about the models they were making relative to global warming at the time. They didn't call it climate change. And I went there and it was really interesting. And I worked with the modelers to talk about what kinds of things they predicted. And they told me, and they said that if you worked on this for 30 years, you'd know. But they told me that Washington DC would be underwater 25 years ago. And I was as happy as I've ever heard since then, and to my disappointment, it hasn't happened that way. So that's just a little cautionary tale about making sure that you use these models properly and don't over sell yourself on what predicted outside the plane of the word, what you're coming up with. And I hope we're really intelligent about how we do that.
Absolutely, I think that's a very cautionary note. I want to go to the person online. I think it was Gus had his hand up.
Yes, thank you. Two more questions. One is, can you just comment on how the stream bed and spring elevations were chosen in the model since you have such large grid cells? Was it just set to the top of the grid cell or the lowest point in the stream within that grid cell, the median, the mean? I'm just curious how you chose those.
It ended up being usually the lowest point in that particular cell. And frankly, it was done by hand, which took a long time. You know, I first tried using a digital elevation model and just extracting everyone, but really needed to go in by hand and adjust all those, usually to the lowest elevation for that particular cell to get the base flow to match up. Yes.
Oh, excellent. And then last question. So in your opinion, do you think that there's a strong enough spatial correlation of hydrogeologic properties or hydrogeologic features that would lend itself to subdividing the basins? Because it looks like the ones that were used in the water budget report were mostly geographic features. So I'm just curious, if you were to redo this analysis, would you do things slightly differently?
No, I mean, those north, south, and west basins were just chosen for convenience to like look at certain areas, like, you know, that's come up with a way to break them out, but they were never meant to say really that there's a difference or one, you know, effects wouldn't cross the line from one to the other. Because I see that in, you know, if I overlay those on some of the drawdown maps, you know, they cross those north, south, west boundaries already. So they were just geographic constructs to help understand the water, I would say. But I mean, yeah, I mean, I wouldn't really want to go down the road of dividing it up based on since I don't have to manage things, you know, I wouldn't, you know, I prefer to keep it as, you know, a whole holistic system. And as far as, you know, dividing it up into certain areas, it's really, I mean, the model's set up that you can test all these areas, you know, however you want. So, I mean, it's just a matter of dividing it up in a way that you can understand what you're doing and testing those things, and you can see, you know, if those boundaries are really boundaries or, you know, maybe effects cross, you know, to nearby, to the next sub areas next door, and all that stuff can be tested with the model. I'm sure that'll be done.
Excellent. Yeah, thank you again for the presentation.
Yeah.
One quick question. You said on the modeling, some of your limitations was the well, that they had multiple wells and one of the grids and stuff. How did you decide, did you do a medium of all the wells in that section, or did you just pick one in there and say that's the one we're using for that grid?
It's a summation of all the wells, right? So if there's 2 irrigation wells and a private well, you know, in that top 100 feet, and then they're no deeper, then they all 3, the pumping rate for that cell was the sum of all 3, because that's how much is coming out of that unit of aquifer.
But on the drawdowns, did you do a medium of all 3 wells, or did you just hand pick a well?
For the drawdowns that I showed, they were all the observation wells in that cell. So I plotted the observation well measurements and the cell water level or that observation well was in. You know, so, you know, there's gonna be some, you know, mismatch a little bit, you know, if the observation well is in the, you know, upper left corner, the water level for any cell is in the exact center of the cell, right? So it's in the midpoint of the cell, 50 feet down, right? So it's halfway from 0 to 100. So there's gonna be, you know, not an exact match, but in general, you know, you get the right trends and pretty good matches, especially if there's no pumping in the area.
So all those dots on that thing were just observation wells? All the dots on your things that you did, the cones of depression and stuff, and that were on it, those are just, or were they original?
Those were all just, any ones where I showed a map of water levels and then the well, those were all observation wells.
Okay.
And they're general, because, I mean, they're much better to use than a pumping well that's going on and off, or even the winter level, things like that. So, you know, an ideal point is an observation well, you know, miles from any pumping, right? That's gonna kind of give you your best guess. But if, you know, if your observation well is 30 feet from a pumping well, open at different intervals, you know, there's all kinds of complications. But I mean, generally, you know, the model is a generalized version of all that. That's why you don't want to, you know, predict, you know, different water levels 100 feet away, or this well or that well kind of thing. And, you know, I wouldn't use the model to, you know, to go pump well A and look at well B 1,000 feet away and say, well, the model says it's gonna draw down, 10 feet or whatever. It's not designed for that. It's more these big regional, looks at things.
And so when you showed hydrographs that were like simulated hydrographs,
Yeah,
from your perspective, you're more looking at what the trend line is, and if it continues to decline or if it flattens out, then you are what the absolute value is, right? Is that fair to say?
we go for both.
Okay.
Yeah, I mean, in some cases it's less appropriate, but in any case where there's, the observation wells are mostly penetrate through, a whole layer, things like that, so if the observation well is open to 300 feet, I would average the water level in the top 3 layers of the model to match that. In some cases, some wells are constructed in some way you don't quite understand, you don't know where the water is coming in. So a lot of the complication, especially with the pumping, is, you kind of got to generalize it, but if somebody drills a well 300 feet and they hit good water the last 20 feet, they stop there. They might leave it open for 200 feet, but really, all the water's coming in that bottom 20 feet, it's hard to represent that exactly. So there's lots of, deciding, what units the wells are really drawing from and things like that. So, I probably looked at least 2,000 well logs, the geology of each, and to make sure, see why they react the way they do.
When we were looking at the time lapse from 1930, 2018, it was only the top 100 footage top layer. You said we could produce maybe the top 5 layers. Is that something you could help us with?
Yeah, or we could show those guys how to do it easily. We have this rule, but I can't just do something and hand it out, right? It's gotta go through this review process. But the nice part is the model published, other people can download it and run it. So it's kind of, for future stuff, the path of least resistance is to have, guys at OWRD.
To that question,
things like
then,
that.
would there be an opportunity for some of us to sit down with you? I know Nature Conservancy is running some models, Water Resource Department, and Gus might be running some models. To our virtual sit down with you to ask more detailed questions.
Yeah.
Updating the model. So now we know the model was a 2018, but some of us hope to use the model and look at, 10-year review of the RAC and how we update the model with future actions. How arduous is that, Steve, or how do you work through that?
Someone's got the money. It's just a matter of, we want to calculate the next 10 years of pumpage, right? And look at recharge on what might have happened, from 2018 to 2028, whatever. And it's fairly simple since it's already calibrated. You just, okay, let's make up a file, next 10 years of recharge and the next 10 years of pumpage, and plug it in, run the button, and look at the results.
Can you give me an estimate? I mean, this is Tim's honest question. If we're gonna try to find funding to do the model, the first thing we need is an estimate. I mean, that's not realistic, unrealistic.
I completely agree.
Okay.
I don't know that this meeting is the meeting, in which to have Steve,
I'm not,
pull out a napkin and write down some
I,
numbers.
Steve knows me well enough. I wasn't asking for an estimate in this meeting.
I also know
Steve and I worked.
I know I'm not allowed to ask you for money because of your position either.
And but everybody knows that's what I'm garnering at. We were able to get money from the federal delegation with the USGS to help with House Bill 2018. We've been able to get funding for USGS to do projects. So that would be my goal. I'll stop you without Tim. Results in accuracy of the model. I mean, when we read through it, we saw some of the accuracy model. Was there an accuracy model done on it? Is that?
Not necessary to know. It's really just the, what's published is kind of the, some areas you feel better about than others, it's kind of hard.
Well, your calibration stuff was a little bit of accuracy, right? I mean, you formed the model by using data that you have, but you never then saved back part of the data to be able to predict the data from the model.
No, because I want to use all that data to
You didn't-
calibrate
yeah,
it.
You used up the data, you didn't, to make the model, you didn't try to predict any of the data with them, what you made, so.
I mean. Yeah, I mean, I'm
I mean, that's what
predicting,
that's what an
predicting all
accuracy
the,
assessment.
I'm predicting all the data with the model and it matches it, you know, so that's gonna,
Yeah, you made it match though.
yeah, that's.
That's what you said, you made it, so, yeah, it matches. But it had never predicted anything accurately.
Well, I mean, the physics
Well, you
works.
don't- we don't wanna have that discussion, we just don't.
So we've come up on, yeah, we've come up on time. So I want to thank Steve, and the USGS for their presentation today. Thank you, Steve. Thanks for answering all the questions, digging in here. Thanks to all of you who came out and, listened and asked good questions, as we all try to learn together. The RAC meeting will start at 1, so in an hour, you go grab lunch or whatever needs to happen. And yeah, thank you all.